if you have the code, please let's be together if you have the code. All right. So I will go through the codes to highlight the steps involved in parameter estimation. But I am using LSE. Okay. So the first thing to do is to load the required package, which in our case is what? deSolve, right? So you run that. The next thing is to do what? You add the code. I want you to tell me. Do what? Import your what? Data. And I told you should note that you use your own data parts, right? Is it still a no answer? Okay. All right. So read the data in. The head and tail is just to take a look at the first 6 rows and the last 6 rows. So you can check that to see of the data. So with that, you will notice that you have on column 1, day, and column 2, what? What's on column 2? Flu, right? Okay. And then you can check the last 6 as well using tail. Are we together? Are we together? Okay. Now plot to view the data, just to see how the data looks like. Okay. So this is the data. I believe you have this as well. Yeah? Can I get a question? Well? Yeah? Yes, data flu. I've sent data flu to you since morning. So read in the data flu data. Right? How many of us have this plotted? Okay. People at this side, they don't want to do the exercise this afternoon. So they have decided to let me alone here. But I'm not getting responses from you. Okay, so in the plots, you will see that, I showed from the head that we saw, you saw that the data has on the left, on the first column as what? Flu, right? The second, day, and the second column as what? Flu, right? Good. And now, I just want to plot this to see how the data looks like. So I say plot. This, if you use this way of plotting, that means this will be on this is y-axis against what? X-axis. Are we together? So the name of the y-axis, right? Tilde. The name of the x-axis. Are we together? From what data? From data named what? Cases. Can you see from the data named cases? And then what type? I want both line and point and circle. And then I want both line and circle. And then I want x to be labeled day and y to be labeled I of t. And so I have this plots. So please, can I have, how many of us got these plots? Okay, good. So that is the data, right? Now, I said that in the morning, this is where the twist is. If it was statistical model, right? I will just look at this data, right? Are we together? I'll just look at this data and see the way the data behaves, isn't it? This one, I can even think of a quadratic equation, right? Isn't it? I can think of a quadratic equation and write at squared plus bt plus c, isn't it? In that case, I've not considered the underlying process at all. All I have considered is what? the way the data looks, right? The pattern in data is the only thing I would have considered in that case. And then I will now estimate my what? My A, B, and what? And C. In that case, I will produce an explicit function, which will be quadratic in nature, right? Because I have used quadratic equation. If I have so used quadratic. Do you understand? That is in the case of functional model, which are statistical. Is that okay? Are we together? But like I said, mathematical model will not look at it this way. Mathematical model is saying that, okay, this data that I have, what is it? It's saying it's prevalence data. Prevalence of what? It's saying it's prevalence of what? Of flu, isn't it? Flu is something that happens due to certain processes. So it's not first and foremost looking at, okay, can we look at the function that applies? No. It's that what are the processes that are involved in flu cases that I am having now? What are the things that produce that? You know, transmission must have produced that, isn't it? Flu must have been transmitted to one person to another, from one person to another for that to happen, which our mathematical model is capable of doing. It's capable of capturing transmission dynamics. Is that okay? It's capable of capturing transmission dynamics with all the factors that are involved. So in this case, looking at it, this flu within just 14 days. So this is a short outbreak, and then we know the kind of model that we can use to model short outbreak. You remember, right? Okay, that we can use an epidemic model without demography, which Dr. Hafiz taught us. Do you remember? Yes. So think of that as a mathematician and come up with that model. So, and having come up with that model, I want to code, first and foremost, code that model, implement that model in R. Is that okay? So that is the model that I've put here, which I called what? Close SIR model. Are we together? And that model, I've told you, is a function of what? T, X, and what? And params, right? Where T there is standing for time, X there is standing for what? The state variables, and param is standing for parameters. So S here is saying that this is the first component of X, right? I here is saying this is the second component of X. Then this R is the third component of X, because I'm dealing with I'm dealing with SIR model. Is that okay? And I have said that this method of coding, you know, it will be long if you're having very long model, right? You can also use the previous one. I said it for this one so that you can see another variant. Is that okay? If you see this kind of code elsewhere, you may wonder that, no, this is not the one they use for us. So it depends on the way the person wants to code. Is that okay? You can code in this manner as well. There are other ones, but at least you are seeing another variant now. Okay, so now what are we doing? Having put the beta, which is the first parameter, gamma the second parameter, then the model equation comes in here, which is ds is represented by what? Minus beta si, right? And that flows to your di, which becomes what? Beta si minus what? Gamma I. And then the gamma I also flows to recovery, which becomes gamma I in the recovery. Is that okay? And what I want to solve is this ds, di, dr. Is that okay? So once I run that model now, I've only run the model. It's the same thing that we do when you supply, for instance, ax plus b. When you supply ax plus b, you have not said anything apart from you specifying that this is the general function that I want to use, right? So in this case, I have just specified the general function, which is the model. Because it has not been calibrated, we have not estimated any parameters. So we are just applying the model alone. Okay, so it's necessary. That's the first step. You know, after you have put in your data, you have examined your data, the next thing is to implement your model in R. Are we together? That is to put your model in terms of codes, line of codes in R. So you run it. So having done that, now okay, I omitted this R code for simulation. I told you when I was teaching in the morning that you may want to run some simulation, just simulate the model. I've taught you issue of simulation to see that the model behaves well. But I'm jumping that step because it's not necessary for this. It was just to tell us that you can first check, right? But now what is next? Now after putting your model is to now also put what we call error function. What do I call it? Error function. This time around, the error function I want to use is LSE, least square estimation. Is that okay? Method. Least square estimation method. Are we together? Are we together? All right. So that function, what does that function do? The least square method, what it does is that it makes use of what we call the sum of square errors. The sum of square error. Are we together? So it tries to minimize the sum of square error between the model and the data. Are we together? Are we together? Okay. So it tries to ensure that the model and the data come as close as possible. Tries to find the value of parameter. What will be the value of these parameters? What are the parameters that we have there? Beta and what? Gamma that I want to estimate, right? What will be the values of these parameters that will make my model outputs to be as close as possible to my data? Is that okay? So now this error function comes in. And then I also told you that because it's a process model based model that we have used, like that of system of ordinary differential equations, such model, you need to know what output of this model correspond to the data that you have. Is that okay? What part of the model output correspond to the data that you have? We have said the data we have is prevalence, right? You will know that as you get the data from wherever you get it from. That may be, okay, this is prevalence data that talks about old and new cases together, or just the new cases alone. So I know by virtue of knowing from where I got the data that this is prevalence data, right? And now I am looking at what portion, what output of my model is also prevalence, corresponds to prevalence. Are we together? And I said for your SIR model, I is prevalence. What does I stand for? Prevalence. Is that okay? From there, we can also extract from that same SIR model, we can extract different other things. We can extract incidents as well, which will be those cases, the parts that flows into I, the inflow. So I will need to create another maybe DK, but since I'm not going that way, don't let me bring that complexity here. Is that okay? But at least understand how to fit in prevalence first. So prevalence. So I need prevalence as outputs from my model to extract so that I can compare that with data. So that's why I will now. So you realize that the end of this code, what is it saying? If you look at the end of this code, which is what this function is supposed to help us evaluate. What is it saying? It's saying out I, isn't it? Are we together? That out is the model outputs. That out is the model outputs. And the model outputs contains, we have the S, we have the I, and we have the R, right? Many other things can be put in case you want to get more outputs actually. But those are the three outputs that we have decided to call out. So now I need I part of it because it's the one that represents prevalence. Is that okay? So, and I'm looking at LSE, which does what? Minimizes the sum of square errors. Are we together? So I say, bring me I component of this model, right? And take the difference between that and the data. That's why you are seeing out I minus cases under minus cases underscore 1. Are we together? And when you do that, when you take that summation, when you take that difference, then we square it. Don't forget we are talking about sum of what? Square errors. So we take that difference, we square it, and then we sum. How do we know? Because now look at it. Don't forget that your data now, you are having 14 data points, isn't it? Are we together? From the flu, we are having 14 data points. 1, 2, 3, up to 14, isn't it? Do you get? Up to 14. Now, if this is what model is producing, that one to producing 1, 2 to 14, right? It's producing, let me call this one data, the first data, right? And then up to the 14th data point. Is that okay? Are we together? Model also the first point from 1 up to the what? The 14th point. Is that okay? Are we together? All right. So now, what we are interested in doing is that what is the data saying? What is the model producing? So take the difference here. Is that okay? Up to this place, take the difference here. So when you take the difference, you have the difference produced. Are we together? You have the difference produced. And so when the difference is produced, you take the square of it. Right? And so when you take the square of it, what do? You sum it. Are we together? And that's going to give you sum of square error. But you know, with different parameter values, you are going to be having different model outputs, isn't it? So with that, we are looking at what parameter value is it that we ensure that we get the minimum of this sum of square error. Do we get? The parameter value, the set of parameter values, beta and gamma, that we ensure that that sum of square error is minimum. Are we together? Because if I put, that's why the other day I asked you to check if beta is so value. Check your outputs, right? You have different outputs, isn't it? If your alpha is different value, gamma is different values, you also have different outputs. So we have different outputs with different parameter values. But we are interested in that parameter value that minimizes that error function. Is that taken? Okay, so with that, this is how we define the error function because of what we need in there. So we put our time, okay, which is the first column of the data. We put cases 1, which is the second column of the data. Beta, which is the first parameter. And then gamma, which is the second parameter. And then initial condition for the state variables. Is that okay? And then we define the numerical solution that we are using ODE here, which I told you the other day that ODE takes, as you can see, something is displayed up there. Is this okay? It's not displaying for you. You have there Y times func palms, and then you have methods and other things. But the first four, Y times func and palms, are the most important. Is that okay? Which you must supply. So here we have used ODE, and Y is necessarily, I told us that it means what? The initial state variable, right? The initial values, right? Okay, so that's why I now put it here that Y is what? Right? For Y, S is what? I is what? R is what? But you know what your S naught is. That means if you take S as what? 762. If you take I as what? 1. And if you take R as what? 0. And then times is taken at what? T. Is that okay? And we have defined our T to be the first component, the first column from our data. Is that not? And then here is the model, which is func. I could have just put func. And then this is now parameter, which is what? Beta and gamma. And this is the time step for our differentiation. And then once that output is gotten, then we define the sum of square error. So if you run that, run it. Is that okay? Now it's also saved in the memory that I have defined the sum of square error. So number one thing that we did was to bring in our data. Number two thing that we did was to define our model. Number three thing that we did was to define our error function. And then the number four thing that we do now is to write our algorithm. Is that okay? Which again I run here, and then by the time I run the initial guess of the parameter values gamma and beta, I supply that into optim. Optim takes three things essentially. One is the initial guess of the parameter, the function that we want to minimize, which is the sum of square error, and the data that we want to use. So it takes those three things. So primarily. So once I supply that and then I run that, so it has already minimized that function. Is that okay? Error function. So, and it has, having minimized, now once I run this now, it's telling me the parameter values. Do you see that now? The parameter values that give the minimum error of that sum of square error. So once you do that, also we are now saying that sometimes the first set of parameter returned by optim may not always be the best. So you can return the parameter that were estimated. The first one, you know, I put it as fit O, then params, right? Yes, you can use it again. The optim should still repeat that process again. So once you do that, run it again, then you generate the next. So again, it's now telling us this is the estimated value of the parameter values. So now, having gotten that, what do? Finally, we plot the model outcome against the what? Against the data. Don't forget, this is our data, isn't it? Are we together? Then I just define what my T should be. And the model prediction, what is it? The model prediction here, you know, again, you see, so you run your model prediction and then put the legend there. So, and you have that. And once you are able to obtain your parameter values, you can do a lot of things with it. For instance, I can get my R naught if I want to estimate it. So I have my beta, I have my gamma estimated already. Don't worry, you don't have these parts in your code. I have my beta, I have my gamma estimated already, and I have so I just put it as a list, and then I know that my R naught is beta over what? Gamma. So with that, I estimate my R naught and run it, and it gives me 0.05. So with this kind of R naught, what do you think? Is it greater than 1 or less than 1? What do we expect of the disease? It should die out, right? Is that not what is happening? That's what is happening. So, all right. Thank you.